Okay, hi Year 12. So this video is looking at the auxiliary angle method with our trig functions, and it's relating back to 11B in Cambridge. So before we actually go into any details, let's look at actually what that means, what it means to have an auxiliary angle. So what the auxiliary angle is looking at, it's looking at basically the sum of the sine and the cosine functions. So graphically, we've looked at adding and subtracting and multiplying the sine and the cos curves in year 11 in extension 1. And if we have a look at the diagrams below, look at that first one there, where we're adding the sine and the cosine curve, we're getting a resultant curve, which is the green one. So that's our added curve. And it looks similar to a sine and a cosine curve. So we could actually write the addition of those curves as either a sine curve or a cosine curve that's going to have a different amplitude to the original and also be pushed over by a phase. So we're basically finding what that phase is going to be and what that amplitude is that's going to make the addition of those two curves this curve here. So our resultant graph of adding those two, we could write as either a sine curve or a cosine curve with an amplitude which we're going to call R and a phase which we're going to call alpha or something like that. And that would happen also for subtracting the curves and multiplying the curves as well. So graphically we also want to, algebraically we want to also think about the complementary angles below. So we know from earlier on in our junior school that cos of 90 minus theta is the same as sine of theta, and likewise the other way around as well. So if we had cos of 27, we've got sine of 63. So that's going to come into play a little bit as well. So what we're basically looking at in the auxiliary angle topic is a function of the form a sine of x plus b cos of x. We're going to be given something like that, and we're probably going to be asked to write it in one of these four forms below. An amplitude times sine of x plus or minus, auxiliary, and likewise with the cos. So we're going to find out what our R is. We can read off what our A and B are. But what I want us to do is when we get questions like this, I want us to expand what our resultant equation is going to be and equate coefficients on the left and the right hand side, which I'll show you how to do, and then we're going to solve. There are other ways to do it, but I think this way is foolproof. You don't have to memorize too much, and there's a lot of understanding involved, which I think is really important. It's also the way your textbook is doing it. Okay, so I'll just jump back to our notes. So let's just do a quick little proof. Given that a sine, I'm going to call this theta, I don't like phi. Given that a sine of theta plus b cos of theta is equal to r sine of theta plus alpha, alpha is our auxiliary, we want to prove this. So r is going to be the square root of a squared plus b squared. So if we have, put my alpha down here. So if we've got that written in a triangle, a and b, alpha's down here, we can work out what our r is. So if I pop in my r into that equation over here, what I'm going to have is the square root of a squared plus b squared, and then that's multiplied by this expanded. So if we look at our HSC formula sheet, the expansion of this is going to be sine theta cos alpha sine theta. And I've just popped this alpha back up here because it mismatches my diagram. So expanding that, popping in our known things, we've got cos of alpha is a on the square root of a squared plus b squared. Sine of alpha is b over the square root of a squared plus b squared. We're going to end up with this. What we can see is within the brackets, both of these terms are over the same denominator. So if I wrote them over the same denominator, they're going to cancel out with our a squared plus b squared over the top. So we're only going to end up with sine of theta times a plus cos of theta times b, which I'm going to write like this, which is the original equation we had up there. So that's where that comes from, and that's kind of what we want to do along the way today. Now, there is a way that we can look at tan of alpha being b over a, and then what we can also do is remember all of these things here. I don't want to do that. That is a shortcut, but I find memorizing that gives us something else to memorize. So I'm going to use the stuff that's written in green. It's going to go from first principles. I think we're going to understand it a lot better, and it's going to be a little bit more work, but I think a little bit easier for us. Okay, so we're going to write 3 sine of x plus 3 cos of x in this form. So I'm going to do it the method over here, and we're going to talk about why we're doing it. So I really want us to understand why we're doing this. So in this form, we've got to read off that our a is 3 and our b is 3. So in front of the sine is a, in front of the cos is b. R is going to be the square root of a squared plus b squared, which is going to be root 18. If you're using the method up above here, you can straight away go and pop in tan of theta, and you're going to get 45 degrees. And in this case, it's going to fall straight out and go back into here. That's not always going to be the case, so I'm going to take us over here to the method that I would like us to use, in which case we will be able to understand more complex questions and have less room for error. Okay, so what I want us to remember is x is a variable, okay, in this question, okay, because it's x plus this theta, and the theta here was what we called alpha above. That there is our phase, or our auxiliary angle. So what I want to do is expand the form that we want to pop it into first. So expanding that using our HSC formula sheet, we're going to get r sine of x cos of theta, cos of x sine of theta. Our r is our root 18, so I popped those in there. Now that is going to be equal to what we originally had. That's the question we were given, 3 sine of x, 3 cos of x. Now what I want to do is I want to equate both sides of that equation. And what I can see is that I've got a sine of x here, and I've got a sine of x here. Now, because this theta is a known amount, cos of theta is a constant, really, isn't it? So, root 18 cos of theta is the coefficient of sine of x, and that's going to be equal to 3. So, I'm going to write this term down here, okay? Root 18 sine of x cos of theta is equal to 3 sine of x. And in doing that, I'm basically equating the coefficients. I'm removing the sine x's from both sides, and I'm going to get root 18 cos of theta is equal to 3. And what I'm going to end up then is dividing by the root 18, inversing my cos, and I get theta's 45, which is what we got before, yes. But in this case, there are no errors that we could possibly have made. And I can do the same for the other part of my equation, the cos part. Okay, so I'm going to equate this side here, because it's got the cos of x, which is our variable, with this cos of x, and I'm going to get root 18 sine of theta equals 3, and also theta's 45. Now, both of these are positive, so we know that it's going to be our base angle, which is 45 degrees, which is in our first quadrant. In this case, it's very simple. It just goes back, and we've got the same answer we got before, root 18 sine of x plus 45. So that's a fairly nice, simple, straightforward question. Let's go a little bit trickier. Okay, let's have a look at this one. Okay, so we're going to write 3 sine of x minus 2 cos of x in this form. Okay, so if you choose to memorize the things up above, that's fine. I'm not. I'm going to equate after expanding. So we're going to expand the form that we want it to be in. On your HSC formula sheet, we can expand this one straight out to this, okay, using our combination of sines and coses. We're going to work out what r is. So over here, r is the square root of a squared plus b squared, which we're going to end up with as root 13. Popping that in, I get root 13 sine of x cos of x minus root 13 cos of x sine of x. That's my expansion. This is what I originally started with. Okay, there's my a, my b is minus 2. I'm going to equate coefficients. So remembering the x, which is that part there, is a constant, okay, because that was in here. In changing it from the addition of the two curves to one function, we're getting a variable thing. The x is not the constant, sorry. The x is the variable and this is the constant. I'm having a good day today. So in equating those sides, we've got the sine x here and a sine x here. So let's take all of the left-hand side with the sine x in it and all of the right-hand side with the sine x in it, the sine x goes away, and then we're basically looking at the coefficients of those terms. So cos of my theta is 3 on root 13. So theta is 34 degrees. Okay, that's the auxiliary angle, the phase, that's our constant angle. Similarly, let's equate the other side, and we're going to get sine as being 2 over root 13. So both our sine and our cos are positive, which means we're in that first quadrant. It's now just our base angle. So popping that information into our question, which had this form here, we're going to end up with root 13 sine x minus 34 degrees. Okay, let's go and do another one. Okay, this one's a little bit harder. So what we're going to do is we're going to be looking at solving this one. Okay, but in order to solve this, I guess in a question you might not know straight up in a HSC exam or a trial that it is an auxiliary angle question. But if you have a look at that and you try to solve that in any other way, so if you try to move the cos x over to the other side, you're going to get 3 sine x is equal to 1 minus cos of x. We can't do that. If that was a 0, maybe we could look at that and do it a different way. But we don't have anything to substitute in for sine or cos. We don't have any squared angles. There's no double angles we could do in there. So what we want to do is look, okay, we're adding two separate graphs together. So in that case, let's look at it as an auxiliary angle. And we need to make sure that we're thinking about it in, again, the whole domain of 0 to 360 degrees. So let's think of it first without the equal to 1, and let's see if we can write the 3 sine of x plus cos of x in a simpler way. And that's our first thing that we're going to do. I'm going to use r sine x plus theta. So I'm going to expand that and end up with this here. I know that my a is 3, my b is 1, so my r is going to be root 10. So this could be written as root 10 sine of x cos of theta, root 10 cos of x sine of theta using the HSC formula sheet. Let's equate both sides, or equate coefficients is what we're basically doing. So I've got my 3 sine of x, okay, and that's going to be equal to my root 10 sine of x cos of theta. The sines are cancelling out, so I'm left with 3 over root 10 is going to be equal to cos of theta. Well, it's cos of 5, but I'm going to call it theta. So theta is going to be equal to, let's pop that in the calculator. Okay, so that's going to be equal to 18 degrees. So let's look at equating the other side. Now I'm going to write that down a little bit quicker this time. I'm going to write that as we've got cos of x up above here. Okay, and that is going to be equal to root 10 cos of x sine of theta. Okay, so in doing that, we're seeing that we've got sine and cos both being positive, so our base angle is 18 degrees. So we know that we can write this as root 10 sine of x plus 18 using this format here. But remember, that's not our answer to the question, because what we're trying to do is we're trying to solve this equal to 1. So I've now found a simpler way to write the left-hand side, and that's going to be equal to 1. So we've got root 10 sine of x plus 18 is equal to 1. So let's solve it. Let's divide by root 10. So x plus 18 is 1 over root 10. Now this is positive. Okay, so we're going to get multiple solutions. So we're going to be positive there and positive there. So we need to think about that. Again, we often forget that. So what we want to find out is what x plus 18 is, and that's going to be the inverse of sine of 1 over root 10. And that in the first quadrant is going to be equal to 18 degrees. And in our second quadrant, we're going to take that away from 180 and we're going to end up with 162 degrees. Okay, but that's not our answer, because that's x plus 18. We want x. So x is going to be found by taking 18 from both of those answers. So what our answers are going to give us are 0 degrees and what's that, 144? And 144 degrees. And that is our answer. Okay, one more to go, I think. One more. Lucky last. Let's have a look at this one. I don't like this one. Look at our domain. No one's going to like this one. So our domain is 0 to 360 and 0 backwards to minus 360. So we've got to think about what that means. Now, first of all, we want to solve this equation. So if we have a look at it compared to the one up above, it's different, isn't it? And, okay, so I'm just going to change a couple of things that I was going to do with this question, because I think what we might do is if we've got a negative in there, let's make our base equation for that the cos equation, if they don't give us one. I just did it with sine. It doesn't fall out as nicely. I'm going to do the cos. So we've got, what have we got? A is minus 1, B is 3. That'll allow us to give us an r of root 10. So if I pop that into my auxiliary angle equation, which is that one, where the r is the root 10, I'm going to expand that then, and I'm going to end up off my HSC formula sheet with this expansion. Okay, so you might want to pause there and have a little think about how we got that. I'm going to then equate coefficients of this equation here and this one up here. So we're not looking at the equal to 1 yet. We're just getting our nice base equation in terms of cos. So for cos, on the left-hand side, I've got 3. And for cos, on this side, I've got root 10 cos alpha. Equating those, I get 3 over root 10 is cos alpha. Similarly for sine, up here I've got minus 1. And down here I've got minus root 10 sine of alpha. Rearranging, I get 1 over root 10 is sine of alpha. So they're my two equations. Let's find what alpha is. Okay, so alpha is 18 degrees rounded. Okay, so if we pop that into our equation, now we can solve it. I've got that root 10 cos of x plus 18 degrees is equal to 1. However, note that our domain up the top there was given in radians, so I need to pop this into radians. Okay, because we can't change that around. So root 10 cos of x plus pi on 10 is equal to 1. Now we can solve it. So cos of x plus pi on 10 is 1 over root 10. Okay, and that's positive. So we're going to be in those two quadrants there. So what does that give us as an angle? So x plus pi over 10 is equal to inverse cos of 1 over root 10. So x plus pi on 10 is going to have two solutions. Oh, it's going to have more than two solutions. Let's look at the first one. Oops. Okay, so our first quadrant answer is 72 degrees, which is 2 pi on 5. Noting that we're also looking at the fourth quadrant. So it's going to be 288 degrees. But we also need to get that one in terms of in radians as well. So that's going to be 8 pi on 5. Okay, so they're basically our answers that are going from 0 to 360. But now we want answers that are going to be going from minus 360 to 0. So what we're going to end up with is minus 2 pi on 5. And we're going to go minus 8 pi on 5 as well. Okay, so what we then want to do is find what x is. So we need to take pi over 10 off each of those, which is basically taking off 18 degrees if we're thinking of it in terms of degrees. Okay, so taking 18 degrees off each of our answers we had up here. Let's fix those up there. Or thinking of it in terms of radians, taking minus pi on 10 off each of those, they're going to be our answers or our solutions to that equation.